In this video, we are going to be talking about iterators in Golang. We will discuss what iterators are in programming, build them from scratch, and see how the new range over function iterators work as part of the 1.23 release of Go. In programming, an iterator can be defined as an abstract entity which provides access to a collection's data one element at a time. The consumer of an iterator does not need to be aware of the structure of the data which is maintained by the iterator. It just has to understand that it has sequential access to each element in the iterator's underlying data structure. Let's jump into VS Code and demonstrate this concept with a basic example. We'll start by creating our own iterator package, which will abstract the implementation away from the consumer. We define a public type called iterator, which is an interface with one method called next. Next returns an integer value and a boolean, which is false when the iteration over the underlying data structure is ended. The underlying data structure, in this case, is a slice. Let's write a constructor for the iterator struct and implement the iterator interface on that struct. As we can see, the constructor creates a hard-coded slice of integers as the underlying data structure. This is to make the example easy to understand. Remember, an iterator is simply an abstraction which allows the consumer to have sequential access to its values. The consumer does not know what the underlying data structure of the iterator is. We will explore this idea more later in the video. The next method returns the value in the slice that is at the index being tracked by the IDX field. This field is incremented each time the next method is called. When the value of IDX is greater than the length of the slice, we know that the iteration has completed and return true to the caller. Let's now build our main function. In our main function, we are instantiating a new instance of an iterator and using an infinite loop to continuously call the next method. For each call to next, the Boolean return value is evaluated to determine if the iteration is complete. Each value is printed to the console. Let's run this program in the terminal. As expected, each value is printed to the console and the program ends. Now let's talk about the advantages and disadvantages of this approach. This implementation demonstrates the concept of pool iterators. The pool iterator approach provides a straightforward way to iterate over the elements of the underlying data structure and provides the control of starting and stopping the iteration to the consumer. When the consumer calls the next method, it is requesting the iterator to provide the next element. While control of the iteration might be advantageous in some cases, that responsibility may be a disadvantage sometimes, as the consumer's code may become more complex with having to process the data it is requesting and be mindful of the state that the iterator is maintaining internally. Let's see how we can transform this iterator to follow a push model. With a push model, it is the iterator's responsibility to feed the elements of the underlying data structure to the consumer sequentially. We can replace the next method with a getNumbers method, which will send each element of the underlying slice through a channel. Now let's implement the getNumbers method. Since we do not need to track the index with this implementation, this field can be removed. With this implementation, we can see that the consumer will be able to iterate over the elements with a for-range loop. However, this code is at risk of leaking a Go routine. If the consumer decides to break out of the for-range loop early, the channel will be blocked. Let's force the consumer to provide a context to this method. With the push iterator ready, let's write our main function. In our main function, we are iterating over the channel that is returned by the getNumbers method in a for-range loop. We have provided the method with the context that it needs to close the channel if the consumer breaks out of its iteration early. In this case, the consumer breaks out of the for-range loop when the value 45 is detected. The consumer is responsible for canceling the context. Let's run the program in the terminal. As we can see, the values of the iterator's underlying data structure are printed to the console until the value 45 is encountered. Let's discuss the advantages and disadvantages of this approach. This implementation demonstrates the concept of push iterators. One of the many advantages of push iterators is that it is suitable for event-driven systems where data is generated asynchronously. Imagine that the consumer in a Go program is a Go routine that simply listens on a channel, waiting for new data to be produced so that it can respond accordingly. A push iterator is more suitable in this case than a pull iterator. The consumer code is also simpler than pull iterators because it is not responsible for controlling the iteration. I would argue that there is room for even simpler code than what we have demonstrated here with our push iterator in Go. Since providing a context to the getNumbers method and having to cancel that context is more responsibility than the consumer should have for a push iterator. This is what the new iterators in version 1.23 of Golang solve. Let's look at a simple example to get familiar with the syntax. From the official documentation, we can see that a new iter package was added to the standard library as part of an experimental feature in Go 1.22. This feature is now available in Go 1.23. There are two new types defined in this package, seq1 and seq2. We will dive into the details of both shortly, but in short, seq allows us to get sequential access to a single value, and seq2 allows us to get sequential access to two values. Let's look at a basic example of seq. The getNumbers function returns an iterator of type integer using the seq type. Because it is the getNumbers function returns an iterator of type integer using a seq. The getNumbers function returns an iterator of type integer using the seq type. Because it is a generic type, we must specify the type we intend to work with. In this case, we are working with integers. Within the scope of getNumbers, the function is iterating over the same hard-coded slice as in the previous example. Again, this is just to keep the example simple. We will look at more complicated and practical examples later in the video. The interesting thing to take note of here is that each value of that hard-coded slice is being passed into a function called yield. If you are familiar with other programming and scripting languages such as Python, you might recall that yield is a keyword which facilitates the creation of generator functions and allows for lazy evaluation where you generate values as needed rather than all up front. In Go, yield is not a keyword, but rather a naming convention for a function which essentially achieves the same functionality. When yield is called on the integer value, it is passed to the consumer of the iterator immediately. We must check the return value of yield to ensure that we stop iterating when it returns false. Yield returns false when the loop body of the consumer calls break. We will see that in action later. For now, we can expect our program to have the same output as our last. Let's run the program in the terminal. Each value is printed to the console as we've seen before. Let's now revise our iterator package to use Golang iterators. Let's first change the interface definition for the getNumbers method to return an iterator instead of a channel. Now, let's implement the getNumbers method according to our new definition. Just as our previous example, the method yields each value in the underlying data structure back to the caller one at a time. Let's now implement our main function. In our main function, we are printing each element to the console in a for-range loop over the iterator. Let's run the program in the terminal. Each value is printed to the console as we've seen before. Let's now look at an example where the underlying data structure is a linked list. This is a basic implementation of a linked list which has an append method for adding nodes to the list. Let's implement a method called traverse which returns an iterator of type node. From the method's definition, we can expect that the iterator to provide sequential access to pointers to nodes in the linked list. Let's complete the method's implementation. Starting from the head of the list, a node pointer is yielded to the caller one at a time. When the value of current becomes nil, we can expect the iteration to end. Let's now implement our main function. In main, we are appending several nodes to the linked list, and then printing those nodes in a for range loop by iterating over the iterator that is returned by traverse. In main, we are appending several nodes to the linked list and then printing those nodes in a for range loop by iterating over the iterator that is returned by traverse. Let's run the program in the terminal. We can see that each node is printed to the console and the program ends. This concludes the basic section of this video on Golang iterators. We will now move on to the deep dive section to break down the sequence of events of iterators, defer statements, and push and pull iterators. This is an example that is similar to the one we've seen before, except we've added a number of logs to help us visualize what happens. In the getNumbers function, we see a value n, which is set to 20. We then see a conditional loop which continues so long as n is less than or equal to 21. There is a log which prints the value of n at the beginning of the loop scope, a log for the case where the yield function returns false, and a log which shows the value of n just before it is incremented. In our main function, we are iterating over our function iterator with a for range loop as we've seen in the previous examples. The difference in this example is that we are breaking when the value received is 21. Based on everything we've discussed about iterators, pause the video and see if you can assess the order of events which will occur for this program. Let's run the program in the terminal. Let's focus on the first three logs of this program. Our iterator shows that the value of n is 20 as the loop begins. The next log that we can see is within the for range loop in main. So, when a value is passed into yield, it is essentially blocked until it receives a return value of true or false. If the for range loop continues its iteration, then the return value of yield is true. We can see that's the case here because we see a subsequent log for the value of n when it is incremented. The value that is returned by the yield function is false when a break statement is encountered in a for range loop. We can see that that is the case for the next iteration when the value of n is 21. The value is passed to the for range loop via the yield function. The for range loop sees that the value is 21 and breaks, and the log for stopping the iteration is seen back in the iterator. From this example, we can see the back and forth nature of code execution between a function iterator and the for range loop that iterates over it. Now, we will look at how defer statements work with function iterators. This example expands the previous. The difference here is that two defer statements have been added, one in the iterator and one in the for range loop. Based on your current understanding of defer statements in Go, what do you expect to happen? Pause the video and think for a moment. The official documentation makes it clear that the semantics of defer do not depend on what kind of value is being ranged over. That is, we can expect the deferred statements in the iterator to run when the iterator function returns, and we can expect the deferred statements in the for range loop to run when the outer function returns. The outer function in this case is main. Let's run this program in the terminal to see this in action. As we can see, when our iterator returns, that is, when the iteration is forcefully stopped via the break statement in the for range loop, the deferred statement runs twice. We know that this happens when the iterator returns because we can see the log just before the return statement is printed to the console before the two logs from the deferred statement. We can see two logs at the end of the program after the log that says exiting. This shows that the semantics of the defer statement in Go do not change because of the type that is being for-ranged over. Let's now have a look at how panics are handled with iterators.
The official Go docs promise that the semantics of panics are the same for iterators as they are for deferred statements. There are no surprises as the semantics have not changed for iterators. This first example shows what happens when a panic occurs in an iterator. In Go, when a panic occurs, the deferred statements are executed in last in, first out order when the surrounding function exits. In this case, the last defer statement to occur is within the for loop of the iterator, and because this is the last defer statement, we can expect it to execute first and to occur twice due to there being two iterations. This will be followed by the defer statement at the beginning of the iterator scope, and then followed by the defer statements within the main function. Let's run the program in the terminal to better understand this. We can see that the defer statements occur in last in, first out order, as we would expect them to for any Go program. When the panic occurs in the second iteration of the iterator's loop, its defer statement from within the loop executes twice, followed by the defer statement from outside the loop. After the defer statements from the iterator have completed, the defer statements from main begin. In main, the last defer statement occurs within the body of its for range loop. Since two iterations occur, the defer statement from within the for range loop execute twice. We then see the execution of the panic recovery, and lastly, from the defer statement at the beginning of main. Let's look at an example where the panic occurs from within the for range loop body. Take a moment to predict the output of this program, where the panic occurs in the for range loop body. Remember that the order of deferred statements is the same as any other Go program. Let's run the program in the terminal. We can see that the deferred statements from the iterator occur first, in last in, first out order, since the function returns before main, and the defer statements within main occur after, in last in, first out order. Let's now talk about push and pull iterators. At this point, each example we have looked at with Go iterators has been a push iterator. This is because the iterator has controlled the tempo of the iteration, while the for range loop body has simply waited for new data to be available. Let's look at how to work with pull iterators. We'll start by building a simple number generator using a Golang iterator. With our generator in place, let's look at how we can pull values from this iterator. The pull function returns two functions, next and stop. The next function returns the next value in the sequence and a boolean to indicate whether that value is valid. The boolean value is false when the sequence's last value has already been returned or the stop function has been called. Let's pull some data from the iterator. Let's run this program in the terminal and see what happens when we move the call to stop around. When stop is called at the end of the main function via the defer statement, we can see that each call to next returns a valid value. We can also see that the call to stop has caused the return value of yield to be false. Let's now call stop after the first valid value is returned and run the program again. We can see that the program panics when trying to retrieve a second value from the iterator. This is because our validity check did not pass. This pull iterator approach provides the control of the iteration to the consumer. Let's now look at a practical example where we will get data from a SQLite database using push and pull iterators. Let's start with looking at the DB package. The course's DB interface has three methods. The method we will primarily focus on is getCourses, but a short summary of seed is that it sets the state of our database for this example. It creates a database with the number of rows that its parameter value specifies. The getCourses method uses the iter.seq2 type to return 2 values to the caller instead of 1, like in all previous examples with the iter.seq type. This is because we want the consumer of this iterator to handle errors. Let's look at the implementation of the getCourses method. The first action of this method is to run a select all SQL statement to query all courses from the database. If an error occurs, we simply return it to the consumer via the yield function in return. You might notice that we are not verifying the value of yield's return value this time, and that is because we already know that we need to end this function early. The next action of this method is to extract the data from each row and populate a course object that is yielded to the consumer. In this case, we are checking the return value of yield. This leaves the power of stopping the iterator entirely in the consumer's hands. This may not be the implementation you want. You may want to end the iteration here by calling yield and returning when an error is detected. Lastly, the method checks if any errors had occurred during the iteration and returns one to the consumer if any were detected. Now that we are familiar with how this iterator works, let's look at our main function to see how to work with it with both push and pull models. In our main function, we can see that the application first calls the seed method to set the state of the database. Once the state is set, it calls the getCourses method in a for range loop. You'll notice that we are now extracting 2 values from the iterator, as we discussed earlier with the iter.seq2 type. This iteration pattern follows a push model. A log of each object is printed to the console. Let's run this program in the terminal. We can see that the iterator prints all 500 courses to the console one at a time. You may have noticed that the loop in main is able to access course objects almost immediately. With iterators, we do not need to wait for all course objects to be parsed and populated into an in-memory container like a slice, which is a much more memory-efficient approach for handling streams of data. I go into more detail on this topic in another video where I analyze the memory efficiency of Golang iterators by comparing them with in-memory containers. Be sure to check that out if you haven't already. Let's now compare this implementation with the pool model. Using the pool model, the consumer of the iterator is using the pull_to method to extract the course object, the error, and the boolean which indicates if the iteration is completed. It is printing each course object to the console, just like the previous example. You'll notice that, in this example, the behavior of the push and pull models are essentially the same. The only thing that has changed is implementation and syntax. How you will decide between which one to use will depend on your application. If you are building a program that is designed to react to some kind of event, the push model may be your best choice. However, let's say that you had a case where you needed to schedule some kind of task based on the data that you get from the iterator, and that the task should only be run every few minutes, well then a pull iterator might be the best option because the consumer needs more control over the timing of the iteration. These examples are designed to give you an idea of what options are available to you, but it is ultimately up to you to decide which option best fits your use case. That's all for this video. Be sure to check out the description for links to the code as well as the blog post that is associated with this video. If you received any kind of value from this video, please be sure to like and subscribe for more Golang content. Leave a comment for any Go topics that you would like for me to cover in the future. I'll see you in the next one.